All right, welcome CHN 308 engineering students to this pre-class explainer. Today, we're taking all that heavy textbook theory and bringing it straight into the real world. This is all about getting you totally prepped for Dr. Toyose Oyagoke's Week 3 lectures on Unit Operation 1. We're going to break down the course source material visually, so by the time you walk into that next lecture, you are 100% ready to tackle some serious engineering challenges.
Okay, let's quickly run through our agenda for today. We're going to cover the Welcome to CHN 308, dive into real-world applications, break down the types of distillation, look at engineering design, zoom in on flash distillation, and wrap it all up with a VLE practice problem.
All right, Section 1. Welcome to CHN 308.
So, as engineering students right here at Amadou Bello University, you guys are learning the exact principles that drive the entire chemical processing world. Seriously, unit operations? They're the fundamental building blocks of chemical engineering, and distillation, well, it's pretty much the undisputed king of them all. This isn't just dry theory we're talking about. This is the actual science of separating mixtures that powers massive global industries, right from your department in Zaria.
Moving on to Section 2, Real-World Applications. Before we get completely lost in complex math and phase diagrams, let's talk about why this actually matters out in the field. Just look at the sheer scale of the engineering you're studying. On the macro level, you've got these absolute behemoths, towering columns of metal dominating the exterior of chemical plants. But peek inside, and it's this incredibly intricate micro-level world. We're talking highly specific trays and heat exchangers that make the actual separation happen. As engineers, your job is to master those tiny vapor-liquid interactions happening on every single tray, just to keep that massive plant from, grinding to a halt.
So, where is all this heavy machinery actually used? The range is honestly wild. You could be at an oil refinery turning thick, sludgy raw petroleum into high-grade gasoline and diesel, or you might be working in a cutting-edge biorefinery, purifying bioethanol for sustainable fuels. Distillation is the powerhouse behind all of it, but it also scales way down to super delicate stuff. I mean, you need distillation to create pure distilled water for pharmaceuticals, to extract those highly sensitive perfume oils for body sprays, to isolate citrus oils for food flavoring, and yep, even to produce alcoholic beverages. The math you're learning right now, it literally applies to all of these incredibly diverse fields.
Section 3. Types of distillation.
Okay, so a huge foundational decision in any chemical processing plant is choosing between continuous and batch modes. Continuous operations run like a steadily flowing river. Your feed goes in and products come out constantly. It's absolutely perfect for those massive 24/7 industrial plants. Batch mode, on the other hand, is a bit more like boiling a single pot of soup on your stove. You load up the still, run the whole process to completion, and then clean the whole thing out. It's way more ideal for smaller, super specialized runs, like in pharmaceutical manufacturing. And of course, you've got to scale your thinking from simple two-component binary distillation all the way up to dealing with highly complex multi-component feeds.
Now, sometimes a liquid mixture gets stubborn and acts like a single component, boiling at a constant temperature. We call this an azeotrope, and standard distillation literally can't touch it. So what do? We use azeotropic distillation. By cleverly sneaking in a third chemical, what we call an entrainer, like benzene or cyclohexane, we can actually break that azeotrope and successfully separate out pure ethanol from water. Pretty clever, right?
Another really advanced technique you'll see is extractive distillation. When you're trying to separate components that have incredibly close boiling points, take toluene and methyl cyclohexane, for example, we introduce a high-boiling polar solvent, like NMP or phenol. This solvent basically acts like a chemical anchor. It alters the relative volatility of the components, pulling one component down the column while letting the other vaporize and escape out the top. It's just a brilliant engineering solution to a really tough chemical problem.
All right, Section 4, Engineering Design. With all those processes in mind, it's time to survey the rigorous design tools you're going to master this semester. Your toolkit for Week 3 and beyond follows a pretty strict progression. First up, you'll tackle the McCabe and Thiel principle. This is a graphical method to figure out the exact number of theoretical stages you need for binary columns. From there, you'll jump into step-by-step equipment sizing, making sure your physical columns won't just flood when you hit them with industrial flow rates. Then comes the reality check, calculating the capital and operating costs, because if it's not economically viable, it's not getting built. You're also going to integrate related mass transfer principles, like absorption and stripping. And finally, you'll bring it all into the modern era by running computer-aided process simulations. This lets you virtually model your complex separations before a single piece of steel is ever cut.
Let's move on to Section 5, Flash Distillation.
We need to zero in on a very specific type of distillation for your upcoming lectures, flash distillation. At its core, this is a continuous, simple, single-stage equilibrium process. Because it's only a single stage, totally unlike those towering multi-stage columns we just looked at, flash distillation offers a pretty limited degree of actual separation. But here's the thing. It is the perfect introduction to the absolute core concept of vapor-liquid equilibrium, or VLE. Grasping exactly what happens inside the single, isolated flash drum is the key to understanding what happens on every single tray of a massive industrial column.
So, how do we solve flash distillation problems? Well, engineers generally rely on two main methods. The first route leverages the temperature and the liquid-to-vapor ratio, using a graphical XY equilibrium plot to track down the exact compositions. The second route takes the given temperature and total pressure and applies strict mass balance boundary conditions to algebraically solve for those fractions. Whichever path you take, you're going to need a rock-solid grasp of your equilibrium data.
And that brings us to Section 6, VLE Practice Problem.
To really test your grasp on all this before you even step foot in class, I've got a specific challenge for you straight from your study materials. Using the principles we just covered, here is the scenario. An equimolar mixture, so a 50-50 split, of benzene and toluene is flashed into a single-stage distillation column at a pressure of 100 kilonewtons per square meter. If exactly 25% of the charged feed is vaporized, what is the precise composition of the liquid and vapor fractions leaving that column?
Here is the raw vapor-liquid equilibrium data for that benzene-toluene mixture. You're going to need this. Notice how the vapor mole fractions, Y, correspond directly to the liquid mole fractions, X. Go ahead, take a screenshot of this, set up your mass balances, and run those numbers based on that 25% vaporization rate. But right before you step into your Week 3 lecture, I want you to ask yourself this. Mastering this single, simple stage is literally your gateway to designing those massive industrial operations we talked about. So if you can't balance the mass in one single flash drum, how in the world are you going to control a 50-tray behemoth? Run the numbers, trust your math, and go prove you're ready for the reality of unit operations.